10 years ago or so when I did this blobs. It was the science of blobology. And we've come a long way since then because now you can actually use radio telescopes like the ALMA telescope in Chile to look at, these radio wavelengths of the dust and these beautiful spiral structures. You can see gaps and rings. There's a lot of beautiful science that's coming out of it. So I don't know if it's as big time as looking for alien life, but it's something that's definitely advancing quickly. And I just love talking about disks because everyone gets really excited about planets. But I think that in the same way that you think like, oh yeah, I'm going to be an astronaut, I'm going to go to space and I can see this beautiful picture of Earth. We'll see these beautiful pictures of Earth. But, you might want the 23andMe of the astronomy world of, where did we come from? What else is out there? And you can get all that information from disks because if you look at a protoplanetary disk, all of that material goes into forming planets. It's, left over from forming a star when the gas and dust collapse. And, most of it goes into the star, but, about 1% or so goes into forming planets. And then long after that gas has dissipated and you formed your planets, you have some leftover material, right? In the solar system, we have the zodiacal dust where planets are, and then further out, we've got the Kuiper Belt, which we know is your favorite for giving Pluto a hard time there, Neil. So.
And one other thing about the disks, it was only 1% goes into planets. Where does the rest of the gas go?
So most of the mass, right, from that gas cloud is going into forming the star, right? And then you've got a lot going into forming the planets. So a lot of this is going to dissipate in time, right? The star has UV radiation that's going to interact with the material there. Some of it's going to blow away.
Oh, wait. So maybe I misunderstood. So the 1% number you gave, is that 1% of the disk mass or 1% of the cloud, the total cloud mass, the protocloud?
Right. Okay. Sorry. So I conflated two things there. So of the protostellar nebula, you have about 95% of that mass goes into the star and the rest goes into the disk. And of what's in the disk, about 1% is solid material, right? So it's the little dust and grains, and the other 99% is gas.
Got it.
And so you've got these couple stages of disks. You've got that protoplanetary disk early on, and later on, after that gas goes away and you're left with the planets, you have things fighting each other and colliding. And that's what gives you debris disks like the Kuiper Belt and the zodiacal light here in the solar system.
So now update me on the latest from JWST, because that's been going like gangbusters.
It's so cool what we can finally see from space. So they were actually able to use the near-infrared superpowers of JWST to actually see water ice and crystalline form in this debris disk around a star called HD 181327. And this is really exciting that you can actually see water ice in a debris disk because in the Kuiper Belt, we've got all of these dirty snowballs, right? We've got the comets, all kinds of icy material. And there's been hints of this from the ground before, but we've never actually been able to see it. So when they took a look at the light scattering off of this disk and compared it to what we see in the Kuiper Belt, it looked pretty similar. You've got these dirty snowballs. And so what this tells us is that Kuiper Belts are not just something that we only see in the solar system. They might be kind of common.
So you found a Kuiper Belt in an exoplanetary system.
Exactly.
Very cool. All right, that's with JWST.
That's right. And so it means that there's all kinds of icy material out there just waiting to form planets. So water might be more common in the early solar system.
So that somewhere out there's another Neil deGrasse Tyson just missing another Pluto.
Because there's a Kuiper Belt waiting for that to happen in there. No, I'm not. I was an accessory to the demotion. I was not. I didn't pull the trigger on that.
Get ready to leave the world behind because on Paramount Plus, Star Trek Strange New Worlds is back for an all-new season of genre-bending adventures, romance, mystery, action, space zombies, special guests, this show is going where no show has gone before. One show, infinite adventures. Don't miss the new season of Star Trek Strange New Worlds, premiering July 17th with new episodes on Thursdays only on Paramount Plus.
So this is fundamentally a Cosmic Queries edition.
It is.
And we solicited questions from our Patreon fan base
They've sent in a fantastic assortment of questions.
on this subject. Well, let's bring it on. Go.
Well, I always like to start with, I think it's always fun when there is a young fan. So Hugo Dart from Rio de Janeiro says, with my 7-year-old daughter Olivia, who is also a big fan of Star Talk, here is our question. What do you find most surprising or humbling about the current state of knowledge of exoplanets compared to when you first entered the field?
Good one.
So obviously there's so many more exoplanets now than when I started, 20 years ago. But I think what's really humbling is the fact that we keep finding new worlds in places where we've looked. We thought, oh, we've already found what's there. But then you find another one. For example, James Webb's recently found some planets in a system where they're puffy planets. This is Kepler 51. And suddenly they said, oh, there's one more that we missed. The Kepler spacecraft was up a while ago, and we're still analyzing that data and finding new information. And the fact that we can find worlds that are so different from our own, right? There are these ocean worlds, there are these lava worlds. It's all just so spectacular that it's really exciting, but also kind of humbling to find that diversity of planets. It's like a zoo.
Did you not expect that diversity?
I think for so long we assumed everything looked like the solar system and Earth, right? Because it was all we knew. And in the solar system, we don't have worlds covered in lava. So the fact that that can be out there, that's great.
Well, while we're talking about different types of worlds and things that look different, Adrian Martinez from Houston says, my question is it possible for a planet to naturally form in a donut shape, like a torus? And if not, what are the weirdest or most unusual planet shapes we've discovered in the universe so far? Do we even know? Do we even know the shapes of a lot of these planets? Because a lot of the time you're just going on mass, aren't you? Or can you see a shape? I don't know.
So that's a good question, Adrian. I don't think it's possible to form a donut planet. Neil, correct me if I'm wrong, but that seems hard with gravity concentrating everything. And the easiest shape to be is round because it pulls everything in nice and tight.
I wrote an essay back when we opened the Rose Center for Earth and Space, because in the middle of this facility is a round thing. Okay, there's a sphere. So I wrote an essay called On Being Round. And it was all about how nature just wants to make things round. And when it's not round, there's a really interesting reason why it's not round. But I don't think we ever get anything a donut, because the gravity wants to put it all in one place.
And it wants to put it in the middle.
In the middle, exactly.
I was just going to say, there is, a really cool planet called WASP 12b, that's sort of egg-shaped, right? So I think that's pretty cool because it's really hot. It goes around its star almost, once a day. And because it's so hot, it's actually tidally locked and it's getting stretched. So not only do you have this planet that's like an egg, it's not perfectly spherical anymore, but it's actually giving off mass. And so we often find that planets can actually disintegrate a little bit and leave a torus of material from where they were. So you don't get a torus-shaped planet, but you have the leftovers in a torus, which is pretty cool.
And what about was it a comet or an asteroid that looked like it was two spherical pieces stuck together? It looked like a dumbbell, like there were two. So you can get that, but it didn't form that way.
So it formed as two round things, and then it sort of,
and
they
then
kind of
came
met.
together. I think that's the understanding of
Well, so you can get all kinds of weird shapes in asteroids and these smaller bodies, because it's when you get up to being a planet when you have so much mass, then you're becoming round and forced to sort of circularize.
Oh, because the smaller things have less mass?
Yeah, they have less mass and gravity.
Right.
And so the rocks win. Whatever the rock is doing, it stays that way.
Well, there's a couple of questions here about habitability that I like to combine questions sometimes if they're on similar topics. So William Warren from Abingdon, Maryland says, what exactly defines a planet as potentially habitable? Is it just being in the habitable zone where liquid water could exist, or should we consider atmospheric composition, magnetic fields, plate tectonics, and more?
Love it.
And then also, Sean Browning from Hood River, Oregon. When our star inevitably expands and consumes the inner solar system, what effects would that have on the remaining planets, and what planets would fall into the new habitable zone?
Ooh.
Or would the expansion of the sun change the remaining planets' orbits, or would the mass not change, therefore leaving the planets in the current orbit? So what makes a planet habitable, and how will that change as the sun starts to
I love it.
swallow our worlds?
No, that's such a good question. I mean, right now we use the term habitable zone, but really that should, the long, the asterisk, read the fine print should really be region around a star where liquid water may be possible and seen on the surface. So just because a planet is in the habitable zone, that just means it's the right distance from the star where liquid water could hopefully persist on the surface. So sometimes people talk about the distance from Venus to Mars because, in the past these looked different. But people use different definitions, and part of how we think about habitability on a planet is involving liquid water, right? Because that's what life on Earth uses today. But there's so many other factors, right? So you need water, you need energy. So starlight, all that UV radiation is good stuff, right? Makes the crops grow, but too much, and that's a problem. So if you've got, the stellar wind and all kinds of stellar flares from your star coming and beating down on you, that's bad news. So you want just the right amount of energy, and then you, of course, need nutrients to make everything happen. So I think there were some questions in there about, what happens as our star changes, right? And our relationship with our world is not the same. And I think, where the habitable zone is in the solar system today is not where it was in the past, and it's not where it'll be in the future. Because it used to be a little closer into the sun. That's why Venus used to be wetter than it is today. You had more Earth-like conditions, and then, of course, you had this runaway greenhouse effect. And now it looks kind of hellish. And so in the future, we expect as the sun gets brighter and expands out, Mercury and Venus are actually going to be sucked into it and eaten up. But we should be okay. But out by Saturn is going to look pretty good for habitability. So maybe Titan, the moon around Saturn, could have a good day because it's got a lot of methane in its atmosphere, kind of like early Earth.
I heard this and I didn't believe it until I did the calculation, that when the sun becomes a red giant and Earth is long gone, so is Mercury and Venus, and Mars becomes uninhabitable as a hot zone, Pluto becomes a habitable place.
Right.
I heard this, and I double-checked it, and it checks out.
The numbers crunched correctly.
They crunched correctly to make a Pluto a place where we might all have to escape to survive. There'll probably be a picture of me at the immigration.
No entry. Just you get taken into the second room.
Aren't you going to be reconsidering your life choices at that point?
We've found some things you've said, and we'd like to ask you some more questions. Speaking of more questions, Ben Grund from Detroit, Michigan says, I hear it sometimes said that our solar system is pretty atypical in its constituency. Is every solar system a snowflake, or are there some common themes to their layouts?
Well, I like that.
Well,
Good
we were just talking about the debris disk with water ice. So we do have some snowflakes out there in other systems, quite literally. But I think the thing that we originally thought was that everything was like the solar system, and then we found always these big planets like Jupiter close into their star, hot Jupiters, because they were easy to find. We discovered that actually they're nothing like the solar system. But over time, we're finding more elements that are pretty similar. So I think that we can say that we are not, totally unique, but totally dissimilar. So I like the snowflake analogy because I actually think that there's enough similarities and differences for it to work for us. Also, people just tell me I'm a special snowflake. I love the fact that you have exoplanets discovered all over the world, right? It's not just telescopes in one place. And so you have WASP, right, this wide-angle search for planets that found exoplanets in its early days, and then they've souped up versions. There's Super WASP now. So I think there's even a Super WASP telescope in South Africa. They're all over the place. And this is just one of many. Many of them have awesome names, by the way, right? There's the TRAPPIST ones that come out of Belgium that are making these great discoveries, and then we can keep studying them both from the ground and in space.
God, scientists love a contrived acronym. Nothing makes scientists happier than finding some acronym.
When I was in college, there was a computer scientist. This is early days, before that was even a title. There was some program we were all using, and its acronym was MAGIC. Okay, what does that stand for? What is it? He says, mnemonics are generally idiotic constructions. So ever since then, I've
Yep.
not overdone my mnemonics. So what else you got?
All right, so Ryan Gurrence from Pittsburgh, Pennsylvania says there are many different types of telescopes with a variety of sizes, but none of them have the resolution to actually see exoplanets. So my question is, how big would a telescope have to be to have the resolution to actually see a nearby exoplanet? Could we align multiple telescopes on Earth to make a telescope effectively as large as one of our planet's hemispheres? And would that even be big enough?
Doesn't he? I'm betting, because we do have images of planets. I think this questioner wants to see continents and oceans and cities. What do you think?
I mean, because I'm right there with you, Neil, that we've seen exoplanets already, right? Again, they don't look like Earth so far, and we just got a couple of pixels. Although, as Carl Sagan's famous moniker of the pale blue dot from Voyager 1 spacecraft, and it's out at the edge of the solar system looking back at Earth, you just see a pale blue dot. So we're not yet at the level of continents and oceans, but actually one really cool thing about the Habitable Worlds Observatory, you might actually be able to get a sense of oceans because of how the light, you would have the glint coming off of the water. So to get to the stage of continents is pretty far off. Haven't done the math on what you would need to do that. It seems hard, but certainly we can take pictures of exoplanets now from the ground that are big like Jupiter. And again, with HWO in the future, we'll be able to see the planet itself without that level of detail.
So not to diss Pluto even more, but when you describe this pale blue dot image taken by the Voyager 1, prompted by the efforts of Carl Sagan, when Voyager 1 exited the solar system, that picture was taken when Voyager 1 passed Neptune. That's the edge of the solar system.
Well,
It was well inside of the orbit of Pluto.
Yep.
So the idea was aliens would come upon our solar system and they'd see the first planet, and that would be Neptune. And that's when they take a picture of all inside. So I didn't want people to think the edge of the solar, that they were way out there.
No, it was relatively nearby, right?
Yeah, relatively nearby, exactly.
Because we saw a picture of the family portrait, right? It was taken on Valentine's Day in 1990, right? It's showing the love, right? The love of a couple of pixels here and there.
Yeah. All right, time for a few more, I think.
yeah, absolutely. So Jay Starks from Waco, Texas says, here and reporting for Cosmic Query duty.
Okay.
I've been thinking a lot about how planets in our solar system are impacted differently by the distance from the sun, such as temperatures and the number of days it takes each planet to orbit our Helios. Do all exoplanets follow this pattern with their stars too regarding distance? I'm curious if this is a universal truth for all exoplanets in outer space.
Interesting. I think he's asking, the laws of physics that describe orbits, does it change from one planetary system to another?
I mean, the beautiful thing about physics is you don't have to have a great memory. The same rules apply over and over again, so you just have to learn it once. But I think it's kind of interesting to think about the solar system, because you know Bode's law, right? Neil, right? How back in the day when people were looking for, Uranus and Neptune and things, they would look at the distance from the star, from the sun, and say like, there's a planet at these geometric distances. And so then they found the planet and they went, yep, that checks off. And then they said, oh yeah, we found Ceres, because back then Ceres, dwarf planet, was viewed as a planet. And then they said, oh yeah, there's these other things, and then it didn't quite work. And so we stopped. But the notion of distances from the star having planets is one that people have thought a lot about over history. And I think it's actually pretty cool that when we look out at these exoplanet systems, what we see looks nothing like the Earth and the solar system, and that's partly because they're different systems, but also even within our own solar system, everything moved around. Jupiter and Earth didn't just form exactly where they are today. They did a little dance. Yeah.
So planet migration.
Yeah.
What's going on there? Yeah. So I'm reminded that when Isaac Newton first wrote down his gravity equation, and it worked for Earth and the Moon, it worked for the Sun and Earth, it also worked for Jupiter and its moons. So it wasn't just like a sun thing. It was, oh my gosh. And so that we correctly, though audaciously, said it's a universal law of gravitation. That's kind of bold, but I mean, why not?
Well,
We're egocentric as humans, right?
well, while we're talking about moons, there's a moon question from Fred Dog. That's patron Fred Dog. I don't know if you're from the Westchester Fred Dogs, any relation? But Fred Dog
You know
says,
some Fred Dogs.
it was once thought that habitable worlds had to exist within the habitable zone and would require a magnetic field to protect itself from harmful solar wind particles. However, this has since been determined to not necessarily be the case, as our understanding of habitability continues to grow. Now moons like Enceladus and Europa have become candidates for housing possible life, but fortunately, they also happen to be protected by the magnetospheres of their respective planets. My question, how has the inclusion of moons further complicated the search for life beyond our solar system?
I love that. And I'm going to add to it, will there come a day where we just abandon this concept of habitable zone? Because if the conditions are ripe somewhere else and is not in the zone, it could have life. So maybe the habitable zone concept is constricting our creative thoughts of how, when, and where we might find life.
Yeah, so I mean, it's great that Fred Dog mentions these moons, right? Europa and Enceladus, where you might have this thick layer of ice and you've got all this heating that makes a nice, cozy ocean underneath. So one of the things about the habitable zone, like I said, that fine print, long liquid water may be found on the surface here, right? If there is life under the ice, you won't be able to see it from the atmosphere as we know of now, right? So when we talk about the habitable zone, it's about where could we actually look at our telescope and say maybe there's a biosignature for life here. So it's not saying that moons are out of the question. People are definitely looking at moons. I think David Kipping, who you frequently have on this show, your
Yes.
neighbor down the street there in New York, he's always thinking about exomoons. And
He's
so,
up the street. He's up the street.
excuse me, at my LA
New York
geography.
is very specific about direction.
Yeah. Get my New York straight here. No, yeah, he's up at Columbia, and we're delighted when he's on the program.
So, I don't know if we can detect the signatures of life from a moon yet, but it's one of the things that we want to look for. And actually, the question of does it complicate things? Yes, because if you want to get the signature of a moon, now you have to get rid of all the information about the planet. You can't just say, oh, I'm only seeing the moon there. In the same way that when we study exoplanets, we have to get rid of the star to study the planet. So there's a different level of complexity. And to your point, Neil, of maybe it's time for a new definition. I think it's just, you need something without the asterisk and the fine print of, liquid water at the surface here.
And let me tell you how old I am. So when I was in graduate school, the Voyager mission was doing its grand tour, and everyone was in high anticipation of what it would discover about the planets. And when it started imaging the planet moons, oh my gosh, the moons became more interesting than the planets themselves. And now people don't care about the planets. But Jupiter's moons are way more interesting than Jupiter, by far. I don't know. I'm speaking out of turn here. Tell me, you got to agree with at least some of that sentiment here.
I think that moons are spectacular, right? I mean, I think the fact that, you can look around Saturn and see hundreds of moons, and they all, you've got ones that look like the Death Star, right?
Yes, it's got this big crater in it. It looks like the Death Star bit that would send out the ray. Yeah, don't you guys call it the Death Star moon?
I think we normally call it Mimas, but, we can give different names, sure.
For when no one's listening. When behind closed doors, when you're just over a few pints.
Exactly. So there's all kinds of beautiful things there. But I wouldn't count, how awesome Jupiter and Saturn and the solar system planets are, because there are things we don't understand. Like, why does Saturn have a hexagon at its pole? And, why do all of these outer planets have rings, right? Saturn gets all the credit for, the hula hoops that shine. But, all of these giant planets do, Neptune, Uranus. So I think there's a lot going on there, and I can't wait to see this for other systems.
There's a nice question here from Andy L., who lives just up the road from Anjali and me in Thousand Oaks, California. My understanding of the two main exoplanet search methods, periodic stellar dimming and stellar Doppler wobble, is that they both rely on their star's ecliptic being in line with our line of sight. Does this mean that if a distant star's ecliptic plane is angled off our sightline, neither of these methods would work? Could that explain why some stars don't seem to have planets?
Don't our people ask good questions?
Your people ask great questions, Neil. I mean, and that's one of the best parts of getting to hang out with all of you is it's just the most fun. People say like, it's a secret. I don't want to tell anyone. I want everyone to know how cool exoplanets are.
Oh, yeah.
It answers to the questions. Like once we find life, we were joking earlier, Matt, like I can't tell anybody in my ambassador role, but no, I want everybody to know, call your senators, call everybody, tell them it's amazing. We have two methods for finding exoplanets that Andy L mentions, and it's exactly right that the transit method, right, where the planet is lined up just right to block out the starlight every time it goes around. You do need that geometry to be pretty close to at an angle. We call this sort of edge on. If it was so-called face on, 90 degrees off, you wouldn't actually be able to see that starlight getting blocked. And in the same way, the radial velocity or Doppler wobble method is where the mass of the planet tugs on the star and we go back and forth. And this only works, of course, if that star is moving back and forth from the telescope. So both of these don't work if it's at exactly 90 degrees, or face on as we call it. But if it's even a little bit off, we can actually see components there. And this actually tells us some interesting facts about the mass of the planet, because there's a famous system that was early on detected as a possible planet in the early days of exoplanets, and it turned out that they had that angle totally wrong. Later, when they had astrometry, where they were actually able to look at the positions of the planets, and look at the position, of the stars, they could see it was actually the other way around, and this was actually a brown dwarf, actually even a little bit bigger than that. So the angle matters, but we can get there as long as it's not exactly 90 degrees.
And there's another piece of this where we know the statistics. If these systems are randomly oriented to our field of view, then we will know precisely how many systems we're missing. So I think just because you don't see a planet because it's tipped out of the field of view, we have a way of arithmetically compensating for that. So in fact, we have this number of planets in our catalog, but again, like Andy L said, if it's not lined up, we don't see a planet, even if there is a planet there. So statistically, presumably we know this, and we can scale up the number of planets we detect as if we would have seen all planets around all stars. So do you have a latest planet count for that?
I don't have the exact numbers, Neil, but I'm totally on the same page as you and Andy L, that just because we don't see it today doesn't mean that there couldn't be planets in the system. And that's actually one of the really cool things that the Roman Space Telescope is going to do. Because it's going to be finding planets through microlensing, it doesn't care about the geometry, right? So it can actually look for planets that are farther away than what we do with the transit, where it's nearby and you have to see it regularly. And so we expect we're going to see planets in systems where we thought, oh, didn't see that there, but okay, I guess I could have seen that coming.
Just to be clear, what you were saying a second ago, Neil, you can sort of just assume that planet's orbital plane is evenly distributed in all angles. So you can go like, we can see these angles and these angles, so you can then calculate, well, these ones must also exist.
Exactly. You extrapolate.
Proportionately.
You extrapolate into the galaxies where you didn't see any planets at all. Once you know what fraction of stars have planets that you've detected, and there's all these other planets that don't, then you just look at the statistics of the orientation, and you can fill in those missing numbers if it's randomly distributed out there.
While we're talking about that kind of detection and validation of things that are a distance away, Alan G says, hello, great and mystic diviners of the cosmos. How accurate do we believe these remote measurements and determination of atmospheres and life conditions are when we have no way of validating something 50,000 light years away?
Ooh, those are fighting words. No way of validating.
Show your work.
Well, what does he want to go there and get a beaker, a sample? Like, no.
I love this question, though,
You just
right?
indicted your whole community right there.
But I love this question because this gets at the very heart of what it means to do science, right? Because, of course, we test the heck out of our equipment so that we know what to expect. And so we can say that maybe we trust what's coming out of it. But the beautiful thing about science is you can make predictions, right? Like that you know when that solar eclipse is coming, so you can be the kid in King Arthur's court. And so even though we can't go there and see it up close, you can make predictions about other things you expect to see. Like maybe when that planet goes to another part of its orbit, what might you see? And so I think the fact that you can make predictions and then you can test and then you can get more data, that's magic. I mean, imagine that you could predict the stock market. So I think that's great. I'm not worried about not being able to go there and visit, although I would love to do that. I mean, I just have to wait for pieces of the solar system to fall to Earth and then we can see them.
So I think it was in the 1840s, somewhere around there, before spectra became a tool to understand the chemistry of something from afar, there was a philosopher who, in his thesis, first he asserted there will never be more than the 7 known planets. He just asserted that, okay? And then quickly thereafter, we discovered more planets. But he also said that the stars, in their beauty in the sky, we will know their colors and their locations, but we will never know what they're made of because they're just too far away. That's what your man here sounds like.
All right.
And within a few years, we turned spectroscopes to the stars, and we know exactly what they're made of.
Right.
So I'm not ever going to say we will never know, because I don't know that we'll never know.
If you look at these drawings of the solar system from long ago, right? And, they're still drawing, Saturn is the furthest we know about because, up until the time that America was a country, that was the furthest planet we had known about. But there are some people who draw all of these different orbits and saying there might be other worlds. And you might think it's kind of fantastical, but some people have that imagination. And of course, the data bore us out. So I don't know. I get excited about seeing planets, about seeing disks. Like I said, when they fall to Earth, as long as I'm not a dinosaur, I'm cool with that. But meteorites are great. I mean, did you ever hang out with the meteorite at the White House, Neil? The little one that's there?
Where was that?
So in one of the rooms in the White House, there is on loan from the Smithsonian a piece of the Allende meteorite.
No, I've not seen it.
Okay, I
Yeah.
called up a friend yesterday to check. They said, oh yeah, the Smithsonian just came and cleaned it, but it's still here at the White House.
Yeah, not all of us just hang out in all the rooms of the White House. Just let the record show.
I was just staff, right? You're, a fancy, distinguished guest. Esteemed
No, I
scientist.
did spend a little bit of time at the White House. Yes, I know bits and pieces of the White House. I don't know all the White House.
No, it's just cool though because people look at this and they go, that's just an ugly rock, right? Because it's like a little black rock with white dots. And I used to go and explain to people like, no, this is amazing. This is older than the Earth, right? You've got more than 4.5 billion years here. And this is like if you were baking a cake, right? And you were messy and you got flour everywhere. You bake the cake, you eat the cake. Okay, in this case, the cake are the planets. But, you've got like little fossilized
Same difference.
flour in this meteorite, and it's here that we can study on Earth and sort of observe at the White House. Because it's something that meteorite landed here around the time when we were getting ready to analyze lunar rock samples. And in the end, the meteorite ended up being cooler than moon rocks. So I'm just saying, I'm here for planets in all their forms. As long as I'm not a dinosaur.
By the way, we might still be dinosaurs because we don't have a way to deflect an asteroid. And we'll be, if we go extinct from an asteroid, we'd be the laughing stock of intelligent life in the galaxy for going extinct, even though we had a space program. See, the dinosaurs didn't have a space program.
That we know of.
We just don't know if the dinosaurs called their Congress people to say, hey, make sure you put more funding into that.
Yeah,
know.
they had the beginnings of it, and it was going well, but then it got into trouble. They got into committees, and then they got bogged down with red tape, and you know how things go. And then
Fake news,
yeah, and then money got redistributed, and somehow.
Matt, we got time for one more question. It better be a kick-ass question.
All right. Well, I like this question. Hello, Doctors TNT.
Oh.
This is Nancy from Hell's Kitchen, NYC.
All right.
Are we up or down or across the road from that? Which direction
They're
are we?
down from us.
They're down
yes.
from us. Okay. So Nancy is down from us right now. And Nancy is wondering, have you ever had a simulation give you a result so strange you thought either this is a bug or the universe is trying to tell me something?
So I will first of all say lots of bugs, no ChatGPT in my coding, so have seen plenty of those. But I actually don't think I've ever had a moment of thinking, oh, that's so weird, but instead, oh, that's so beautiful, because I always think it's amazing that we can just code the laws of gravity into our simulations, and then you can watch stars and gas form into galaxies, and you can look at these pictures, these simulations that are, cosmological in scale, and then compare them to real observations, and they look the same. So I think the universe is telling us, you're doing great, you can do a little better on that subgrid physics, but the big scales, you got it going on. And it's just amazing that we can see it on the computer, because if you go back, have you ever seen those tomb ray simulations from the 70s where they actually used different characters like the letter Q and the number 7 as their particles in these really early computer graphics of galaxies coming together? It's so primitive compared to what we have now, but even then it was right. So I feel like at that point you would have been like, my computer is telling me something.
Well, except generally when you have a simulation, when you are simulating something, I like Anjali's point about the fact that you get to put laws of physics into your code. But if you've done that, the code is not going to show you something that is based on some new undiscovered law of physics. You put the laws of physics in it, all right? And so, for me, the most interesting part of a simulation is if I simulate something with my best understanding of all the laws of physics, and it still doesn't match. That means something else is happening in the universe that I have not reckoned in my models. Would you agree that you're more likely to not match the real world because the real world has something more interesting going on in it than your simulation, and now you got to go back to the drawing board of your simulation and figure out what's going on?
I think there's always so much complexity in nature, and we always start from the ground up. And so you always think, oh, there's that more detail I could add. Just like when I draw, I'm not a great artist. I start with a stick figure, and you go, oh, okay, you can add some eyelashes and some more things, but it needs some color. It needs a little bit more. It's just the same way with our simulations. So oftentimes you can think about what's missing here and how do we add that little chef's kiss of color.
Yeah, she mentioned this experiment by Toomray. He's a very famous astronomer of the day. And we saw these galaxies out there that were very disturbed looking, and we didn't know why. There was even a catalog of disturbed galaxies, okay? The Atlas of Peculiar Galaxies. And why do they look peculiar, but we look perfect? We have 2 arm spirals, and are they a different kind of galaxy? And so we had to figure out that these are the products of colliding galaxies. And all the gravity, they distort because they all feel different parts of the gravity at all different times. And Anjali, do you remember how he figured that out? How he did the experiment?
I mean, I have the visual in my mind, right, of the Tomb Ray because it was Aller and his brother, right, who were doing these
right.
simulations.
I'm trying to, was it he the one, or was it someone before him? Because how do you simulate? You don't really have a computer yet to do it full blown. Oh, no. It was someone before him. I forgot who it was.
First figure out the mergers.
Even before Tomb Ray's first computer simulations of this, as Anjali describes, Eric Holmberg, another galaxy guy, he figured out how to do it with light. Because gravity drops off as 1 over the distance squared. Okay? 1 over the distance squared. Now, if you don't have a computer, how are you going to simulate that on a table? How are you going to do that? you can like move everything every moment and they calculate everything. That's too much effort. So what he did, he had light bulbs and light meters, because light drops off as 1 over distance squared, the intensity of light.
That makes sense.
And so the light bulbs were the parts of galaxies, and he took light readings at what the intensity of the light was, and that was proxy for the intensity of the gravity. And you got to see the distortions in the spiral arms of the galaxy, and you could recreate all the messy galaxies that look like puppy vomit on the sky. Back and
Neil,
forth.
galaxies are beautiful, right? I mean, cute too. So maybe you think anything that comes out of a puppy is cute, but
Yeah, puppy vomit can be beautifully artistic.
Okay, that's pretty clever, right? You think?
I mean, it's amazing what people do in all sort of senses, right? It's not just looking at it on a screen. We did that actually this past year where we actually had a museum exhibit and we tried to make it multi-sensory for exoplanets. So I worked with a perfumer and a sound engineer, so we had the sounds and smells to get you in that world. We didn't do any experiments with it, but it helped bring people in different ways, which was pretty cool.
So presumably some of these planets might have hydrogen sulfide.
We did not poison anybody, Neil.
Not to say.
No, actually, the most interesting part of working with a perfume artist is when you said, oh, we wanted to get towards habitability and life. She brought me lots of smells of manure because she said there is nothing more lifelike than manure. So we didn't have the puppy vomit smells, but we had some other smells there that were very
Your
natural.
perfumer brought you manure.
No, smells of manure. Yeah. Aren't you glad you don't work at NASA with me
Just-
smelling?
Yeah.
Thank you for clarifying
Not the
that.
actual, just the little manure scent that you can just dab on your wrist and behind your ears.
Remind me not to buy that person's perfume. Right?
No, the rest of it though was incredible because what we ended up doing is we had smells like rose garden and horse stables and things like GNT on a Saturday night. It wasn't the TNT drink that we apparently need to come out with. But, things that people would recognize. And then the other wall had these smells of, what does lightning on Saturn smell like? Or interstellar space, or a rock garden on Mars, or a clean spaceship, getting you imagining that one day in the future, those smells could be just as realistic and familiar to us as the rose garden where you don't have to read the plaque. And so going from there to then being immersed in the sound bath where the distances of these exoplanets were represented by pauses in the music. It just sort of brought it together. And even though some of the smells maybe were not what you would choose for, going out on a Friday night, it was still pretty cool.
Well, thank you, Anjali, for participating in our Cosmic Queries.
It's so good to be back.
And when you pass 6,000, give us a call. 6,000 exoplanets.
I honestly suspect it'll pass 6,000 by the time this airs. So.
Oh, okay. And you know what I do at every one of my public talks? I ask everyone to stand who was born since 1995, because that was the first exoplanet discovered. And
Which is a lot of people.
a lot of people, yeah, a lot of people. And because they only known life with exoplanets in the catalog, right? Okay. So they're all standing up, and I say, raise your right hand. And they raise their right hand. And I say, I declare all of you to be Generation X exoplanet. And then they sit down.
I love that, Neil.
But again, that just hammers home how absurdly new this entire
Yes.
branch of science
That's
is.
how you began the whole conversation.
Yeah.
Yes. Laura, tell all my friends at JPL I said hi.
Will do.
Matt, we'll see you on your website.
Yeah, I'm on tour, and on Probably Science, we will get you back very soon.
Probably, that's your podcast.
That is my podcast.
Probably
which
Science. Okay.
I'm very happy to steal you for.
I've been on it
before.
only once, apparently.
We're making it happen again.
I've
We're
been
making it happen again.
near my phone the whole time.
Oh, you're a busy man. We need to pick up moments.
All right. This has been another installment of Cosmic Queries. This would be the Exoplanet edition. I want to thank my guests, Anjali Tripathi and Matt Kirshen. Until next time, I bid you to keep looking up.
We learned from Mr. House that the NCR failed to annex New Vegas because House's presence on the Strip was too formidable. Instead, they came to the bargaining table and moved into the abandoned McCarran Airport. We find the McCarran Airport just a bit south of New Vegas, and though the NCR is spread all over the Mojave, this is their regional headquarters. On the other side of the wall, we find the NCR's major camp. Here we see a bunch of trucks, supplies, and tents all over the airfield. Now, we've been here before. We came here to help the NCR defeat Cook, a notorious rapist, and a few other local raider bosses. I covered those events in my video on Cook. You can find a link to all the videos I mention in this one in the description below. But if we follow the road east and then turn south, we find the airport's terminal. This was once the regional airport of Las Vegas. It was crumbling in disrepair, but the NCR had been hard at work fixing it up a bit. We see their efforts on full display upon entering the airport. We arrive in a lobby lined with slot machines. There's a sandbag barricade right in front of the door, guarded by an NCR trooper. Above him hangs a small military aircraft. We need to explore this lobby to get our bearings. We'll start by turning east. We see escalators going upstairs to the right, but if we go to the left, we find a door. This door leads to the office of Colonel James Shute. He is the acting leader of the NCR here in the Mojave. All of his superiors are tied up at the moment at Hoover Dam.
I'm usually good with faces, but I don't think I've seen you here before. What brings you to Camp McCarran?
I'm here to provide support. Is there anything I might be able to help with?
You don't cook by any chance, do you? Farber's doing his best, but it's hard to manage an army with half my staff in line for the latrine. Honestly, we're fighting a lot of fires right now. The fiends keep pressing their position from Vault 3. We've got the Legion breathing down our necks across the river.